Hi, good morning students. Welcome to the next chapter from electrostatics and which is called electrical potential and capacitance. So we'll move to the next chapter which is called electrical potential and capacitance. Okay, like electric charges and electric field, there are not very much complexity in this chapter, but at the same time there are a lot of interesting things will be there. They can introduce lot of confusions in front of you while they are asking the questions. So without wasting much time on this intro part, we'll jump into the topic and we'll see what all the things will be there. Okay, so right on the first heading called electrical potential difference. Electrical potential difference. Okay, potential as such, it is not we can define, but directly if you go there it is a little difficult. What is called electrical potential difference? First I will separate the term. First I'm looking to what is called a potential difference. Suppose if we are at ground level, if we are staying at ground level and we are moved to say an height of 10 meter, now we are staying here for example, then I can say I have a gravitational potential. Gravitational potential means because of height. So with respect to ground it is 0 height and here it is 10 meter height to the top. From here to here it is 10 meter. So I acquired a potential energy of mgh. Mg is my weight. My weight multiplied with the height difference is getting potential. So here we are saying potential energy. Suppose my weight value will be equal to 10. Then I am multiplying mgh. So potential energy will be equal to 10 into 10. If I multiply, what should I will get? 100. But what is the potential energy will be here? Weight 10 and height here is 0. So which is equal to 0. That's what we are always taking the difference of these two. 100 minus 0 which is equal to 100. This is called the potential energy difference. Okay, so here potential energy difference is coming because of the height differences. So it should not be always like that. It may be due to different reasons will be here. But this is something called gravitational potential energy. Or we can say like normal, our simple potential. Gravitational potential energy, we are also learning gravitation also. That is another different formula. But this is simply a potential energy. So potential energy is always occurring due to the positional difference in short. Here it is a height difference. Okay, so this normal potential energy is happening due to height difference, but in general potential for a body is attained potential, which means it is not in the original position, it is moved to some other place. If I moved from one place to another place, I have to have some energy, or I attained some energy, or I lost from some energy. Okay. For example, I will tell you one example. Suppose I am in the ground, I want to climb a bench or desk. If I am climbing some bench or desk, I am spending some energy, right? Suppose if I spend some 10 joule of energy, then if somebody will be asking, what is your energy? What is your potential energy with respect to ground in the chair position? Now, not in the chair, I mean, you are in the bench now. Okay. Initially, you are standing on the ground level. So I am saying I have like 100 joule of energy. Now I am climbing to a bench. I spend 10 joule of energy. So what is the balance energy with me? 90 joule. So 10 joule of energy I spent to climb into the bench. Now somebody will come and ask you, what is the potential energy when you are standing on the bench? The answer is 10 joule, because 10 joule is the energy I spent, and when I am in the bench, because of the height of this bench, there is a potential energy stored in there which is 10 joule. So potential energy is stored or created when I change in my position is 10 joule, and where this energy will be got? Because I spent the energy as an external agent, I spent the 10 joule of energy. That energy is stored as a potential energy. This is like energy conservation. Energy is not created, energy is not destroyed. Energy is transferred from one form to another form. So energy is initially with me, I transferred to the guy who is standing on the bench. Suppose in another example, I have a kit, I am raising the kit and placing on the chair. So I have some energy, right? 100 joule of energy. Kids will also have an 100 joule of energy. Now what will happen? I spend some energy and lifting the kit and placing on the bench. So I spend again 10 joule of energy, but the kid is spend any energy? No, kid is very free. He or she is not spend any energy, so I put it over there. Now what is the energy of the kid? Energy of the kid is already he or she has 100 joule of energy is there. Now because of I am donating some 10 joule of energy, or I am spending 10 joule of energy and placing the kid on the desk or on the bench, so the kid will also getting 10 joule of extra energy that what I have spent to rise he or she into this top of this bench. So now the kid energy is 110 joule, my energy is 90 joule. Still our total energy will be same. When we are in the ground, we are 100 plus 100. Now kid is on the desk and kid's energy is 110 joule, my energy is 10 joule. Still it is same, it is 200 joule. Okay, so energy is conserved, energy cannot be created, energy cannot be destroyed. It can be converted from one form to another form. That's all. So here energy is converted from the energy stored in my body is converted into a potential energy. So the same way. So we'll move to our topic. This is I just give an intro what is called a potential and potential energy. Now we'll move to our topic. Electrical potential. Electrical potential means, suppose if you have a charge Q. Okay, this charge you are moving. You are moving. Okay, let me take 2 points B comma A. B comma A. So 2 points I have in a surface. 2 points. 2 points are located here. Now I moved one charge B to A. B to A I moved a charge called Q. Okay. So how we'll say potential means, potential difference means we are moving from A to B. What is the final point A? What is the initial point B? So VA minus VB, potential difference is equal to work done to move the body from B to A over a charge of Q coulomb. This is called potential difference. In short, simple diagram, simple equations. Okay, so potential difference is equal to final point minus initial point, A minus B. We are moving from B to A. So work is doing from, I am doing some work, and that work is given by B to A. So how much is the energy spent? Work means energy. How much is the energy I have spent to move this Q coulomb of charge from B to A? That energy divided by that amount of charge is called potential difference between A and B. What's the unit of this one? Unit of work is joule. This is coulomb. This joule per coulomb is also called volt. Okay, so the potential difference unit or potential unit is called joule per coulomb, and which is called volt. Okay, hope you understand this concept. So potential difference is equal to the energy spent by moving a body from one point to another body over a charge W B to A divided by Q, and this is a potential difference VA minus VB. So note down this point, very short. Okay, so potential is always we are calculating based on the final. This is a final position and this is an initial potential. So final minus initial. But work is doing from where? Work is doing from initial to final position divided by the charge. Another way of writing this equation is also like this. Initial to final, WIF, initial to final, or IF. Or you can put like this one also, so you will not get confused. WI underscore IF. You can put it like this. Okay. So hope you understood what is called a electrical potential difference. Okay. So it's quite simple. No major stuff will not be there. Just direct equations and direct concept. We'll move to next thing is called electrical potential. Now we know what is called potential difference. We are moved to electrical potential difference. Before that, one thing you have to remember. Normally we'll say ground level. All the ground level, voltage at the ground level is equal to what? 0. No voltage. It is earth. So earth has no potential. So similarly, one concept we are assuming here, not assuming here, it is a conventions. V of infinity, potential at infinity is equal to 0. Always remember like this. Okay, this is one point. Next point, what is called electrical potential? We are going for the definition of this one. We are going for the definition of electrical potential. What is electrical potential definition states that, suppose if I have a point P will be here, I have one charge which is at infinity, a q amount of charge which is at infinity. Okay, so how much work I have to do to bring the charge from infinity to that point? That point is, I am assuming r distance away, for example. The point is at r distance away. Okay, so infinity, I am bringing the charge to the point P. So I can say potential at P, final point, minus potential at initial point. Can you tell me work is doing from where? Infinity to P divided by the q amount of charge. Here we are going to find out the electrical potential at the point P. So Vp minus, what is V infinity? V infinity is 0. Potential at infinity is 0. So this is equal to 0. Work done infinity to P divided by Q. This I am writing as work done. This is another way of writing P to infinity divided by Q. If you reverse this one, you have to reverse the sign. This is one way of writing this one. You can write infinity to P or P to infinity. You can write this stuffs. Okay, now we have to find out work. Now what is called work? Okay, so I am first finding Wp infinity. So Wp infinity. What is Wp infinity? Wp infinity means work. Work is actually what? F dot S. So normally we will say F into S. Okay, so this is work done. Who is bringing the charge from Q to this point? I am doing. I am doing means with respect to the system, with respect to the board system, I am an external person. So for me it is called an external agent. So work done by an external agent to bring a unit charge, this may be an 1 coulomb charge, from infinity to that point. That is actually the definition of electrical potential. We will write the definitions later, but first we will understand the concept. So work done from P to P. So here first question is, in physics work power energy, you are learning the work equations, right? Hope you, when I say the work equation, maybe some of you have remembering what is work equation. What is the work equation? F dot S or Fs cos theta. But there are two things will be there in physics. If work is a variable force, work is a variable force or variable distance. Here if you see, if you are bringing the q charge will be here. Okay, if you are bringing a q amount of charge will be here, we are assuming a capital Q charge is already located here at the position. When you bring the q, both are positive, what will happen? An electrical force will be here, an electrical force will be here, an electrical force will be here. To oppose the electrical force, I am doing what work? External work. So I am doing an external work. Okay, my external work. So my aim is to keep the small q amount of charge nearer to the capital Q amount of charge. That is what is my aim. But electrical force will be here and external force will be here. And due to this electrical force, suppose the body is moved small distance called dr. Okay, so here work, I can say it's a variable force because this electrical force will change. Electrical force and external force are equal in this case, more or less equal. Okay, so more or less equal in the sense external force is the force, I am doing it to overcome the external force. If external force will be higher means body will move it in that direction, and which is more or less equal to the minimum value of electrical force equal to the external force. So this electrical force which is equal to external force will always vary with respect to distance. If I am keeping here, what is the force will be? External force and electrical force, same value, 1 by 4 pi epsilon 0 q divided by r square. If I am bringing here, distance will be lesser. If I am bringing to this point, distance will be lesser. So force will be higher. So force is varying with respect to what called distance. In that cases, we'll use a term called integrations. When a force or distance is a varying parameter, it is a varying work. We'll use integrations. External force. Okay, external force into distance into cos of angle between them. Cos of external forces like this, dr is like this. So angle is cos 180 degree. What is external force? K into QQ divided by R square into dr into cos 180 minus 1. We are doing the integration. Okay. This integration, we are our aim is to find out the potential at the point P. Okay. So potential at the point P means we will change the diagram like this one. P, and this point I am considering as P. A Q charge will be here. A Q charge is already here. This point is P because I'm bringing the charge to this point, not to this point. I'm assuming this is the point this point is at R meter away. Okay, so my limit of integration where I am moving from P, this P is how far away? How far? From R distance away. This is my starting point, reference point. From reference point to the point P, R distance. Reference point to here, infinite distance. So from P to infinity I am moving. P to infinity means what? R to infinity. Correct? P is a point. This is my reference point, starting point. You can assume this is my starting. Always ground is our reference. From the ground we'll say, okay, 1 meter fan is height, 2 meter the bulb is height. Okay, the shelf is of like 1.5 meters. Always we are measuring from the ground, right? So now capital Q is a ground position. With respect to this point, I am bringing a unit positive charge to here. Now I am going to find out what is the potential at here. What is the potential at this point P? P is here, which is at a distance of R meter away from here, and infinite is here. From infinity, this Q is bringing to this point. So I am going from in reverse order. The work is from I have written P to infinity. So P is at R to infinity. Okay. Now we have to integrate these terms. So minus is taken outside. K, capital Q, small q, integral. R power 2. So this will take an R power minus 2 into dr from R to infinity. Okay. So remember this, we actually need what called W infinity P or W P minus, or minus will be there. If you reverse it, this will be there. So keep it in mind. Okay. So now I am clearing the board here. I want to write some stuff will be here. I want to integrate this one. That is my aim. So minus K into capital small q into integral R power n. R power n means R power n plus 1. So R power minus 2 plus 1 divided by minus 2 plus 1, integration limit from R to infinity. So minus K q divided by, this is already one minus. So this minus and this minus become plus. So this will become 1 by R. Okay, limit of integration from R to infinity. If you are substituting, so capital KQ divided by 1 by infinity minus 1 divided by R. So K capital Q small q, 1 by infinity is 0 minus 1 by R. So the formula is K capital Q small q divided by R, a minus signs will be here. Now potential at P, our from the previous equations, minus of W P to infinity divided by Q amount of charge. Okay, so this I am substituting here. So already this minus with this minus, K capital Q divided by R whole divided by small letter q. Q will get cancelled. Potential at P will be equal to K into capital Q divided by R. This is the final equations we got. Okay, so in short, a charge capital Q is placed at some position, and we are going to find out, okay, this formula is very simple. We are going to find out the electrical potential at the point P. Because of what? Because of capital Q. So what I have assumed, what is the definition of electrical potential is that it is the work done. Okay, it is the work done. Actually, we are doing the work. It is a work done over where? The charge. That is a definition of potential, right? W, previously we have seen potential difference is equal to, okay, potential difference VA minus VB is equal to work done from B to A. In your notebook, you can write WB to A divided by Q. So, electrical potential difference means between 2 points. Electrical potential difference means between 2 points. Electrical potential is for 1 point. So in order to define electrical potential at the point P, we have a reference point. Where is that reference point? That reference point is at infinite. So infinite electrical potential is equal to 0. So here you assume capital Q will be here. I am bringing a unit positive charge. Unit means magnitude is 1. You can assume it is Q is equal to 1. Or simply Q. I am bringing a Q coulomb of charge to a distance of small r meter away from capital Q. So I am spending some that energy, right? What is that energy? That energy is external energy. That is opposite to your electrical force. So I am bringing some energy. That energy, you are moving from infinity to P. That P is at a distance of r meter from capital Q. So you are spending some energy. Okay. So you are spending some energy. That energy divided by what charge you are moving? You are moving this charge. This charge is a static charge. This is not moving. Our aim is to find out what is the potential, what is the effect created by capital Q on this point. That is called potential. So because of capital Q will create an effect on this point. What is that effect? That effect is called KQ by R. That effect is called KQ by R. So the potential at this point. Okay. Now if somebody will come and ask you, hey, you told you are spending some energy to move the charge from infinity to the point P. You spend some energy. I am asking you how much energy you spent, how you calculated. To find out that energy, simply to find out that energy, remember this, to find out that energy, you spend some energy to move from infinity to this point. You spend some energy. That energy will be equal to potential at this point. I can say potential at Vp into, always remember like this, potential at this point into the charge in which you are moving. What is the charge you are moving? You are moving Q coulomb. So if you multiply it with the Q, you will get energy. Okay, you will get energy. What is your energy? You know your energy. If this minus and minus will cancel, KQQ divided by R. What is KQQ by R will be here? This is called your potential, right? So K capital Q by small letter R, and you are multiplying with the Q. So you will get the same stuff will be here, right? That is called energy. So energy W is equal to always potential into charge. Potential into charge. Remember these equations. Hope you understood. I have a capital Q charge will be here. I am going to find out what is the effect of this charge at a point P, which is at a distance of r meter away from here. How to find out that effect? To find out that effect is called electrical potential. Electrical potential means it's a work done to bring a unit charge or a Q coulomb of charge from infinity to that point. How much work you have done? Can you tell me that work? Then I will tell you what is the effect created by capital Q on the point P. I can tell you. I am telling I have spent some energy of 100 joule. Then 100 joule divided by the moving charge magnitude. 100 joule energy divided by the magnitude of the charge. If you divide energy by this Q, what you will get? Electrical potential at the point P. That is called the effect of capital Q at the point P. Hope you understood this concept clear, because this is very important. This is very important. There are a lot of questions are asked for Neet and JE examination from this area. We will see a lot of questions also. That time it will be much better clear. But in short, remember, if you have a charge here, simple, if you have a charge will be here and the charge magnitude is capital Q. I am asking you here on this position, this is at a distance of 10 meter away. For example, if you assume it is at 10 meter away, just an assumption only. I know it is not 10 meter, but it's just an assumption. It's a 10 meter. Then what is the electrical potential at this point because of this charge? This charge is capital Q, right? So K into Q divided by 10. Then you will get electrical potential. So how you find electrical potential? You know this is the formula to find out the electrical potential. Now we have derived based on this one. Okay. So remember two things you have to remember based on the discussion so far. Two formulas will be there. The first formula is because V1 sorry, VA minus VB. First we have written, right, V potential difference, electrical potential difference and electrical potential. Two topics, two formula. Electrical potential difference VA minus VB is equal to, can you tell me along with me? Okay, you are watching me, you have written the notes. So can you tell me along the formula? VA minus VB is equal to WB to A. WB to A, work done from B to A divided by Q. One formula. Second formula from electrical potential at a point R distance away from capital Q is what? K into Q divided by R. So two formula in your hand now. Okay, so Vp is equal to K into Q divided by R. So we have learned about electrical potential and electrical potential difference. Now we'll move to the next topic. Okay, next topic is just a note only. Just an what can I say, it's an additional points to you. This work done, right, this work is electrical, electrostatic force or this electrical work energy. Okay, so here you can say, just write a note, it's an additional point. The work, okay, work done by an external agent. Work done by an external agent, right along with me, work done by an external agent is independent of path, For example, I am going to find out potential at A and potential at B. So I can move straight way, path number 1, path number 2, path number 2 and path number like this 3. So always potential at A minus potential at B is equal to work from B to A whole divided by, I am moving the charge called Q. Okay, this is the definition of this factor, right? WB to A. So here this work is independent of path. It doesn't matter you are moving through here, you are moving the shortest distance is called displacement. Whether you are moving in a displacement or you are moving in a distance path, independent. Work is independent of the path. Work done by an external agent is independent of path. This is a quite important stuffs will be here. Work done by an external agent is independent of the path. Okay, just a note, just an additional point for your this one. Okay, so that is clear. Okay, fine. Next one, next note point. Electric field intensity, we know, right? Vector E is a vector quantity, but electrical potential, the easiness of electrical potential is this one. Electrical potential is a scalar quantity. Important on a point. This point is very important. It's a scalar. Electric field is a vector. Vector quantity, and electrical potential scalar quantity. This is important. Which means if I have multiple electrical potentials are there, I don't want to bother about the directions. I can just blindly add the numbers without bothering the directional parameters. That is the beauty of electrical potentials. Okay, based on this one, suppose if I want to find out, let me see one example. Suppose here I have a point, this point is P, at a distance of Q amount of charge will be here, which is at a distance of R1 meter. I have a minus Q will be here, which is at a distance of R2 meter. I have a minus 2Q charge will be here, which is at a distance of R3 meter. So if you are finding like electrical field, we know the electric field with respect to this point, it is towards this one. okay, towards this one, and electrical field, because of plus q is away from that one and minus q is towards that one, so we have to consider the directions if you are finding the electrical field. Yeah, when you find the electric field, you have to consider the direction, whether it is towards the charge or away from the charge. It depends upon the positive or the negative nature of the charges, but here you don't want to consider about the nature of the charges. Okay, so only you have to do potential at P will be equal to, how many charges will be here? 3 charges. Potential due to plus q plus, potential due to minus q plus, potential due to the next charge. What is this one? Minus q. You can blindly add. You don't want to mark any directions at all. Tell me, what is potential due to q? Potential due to q means kq divided by, at this point. So what is the distance? R1 plus. Potential due to minus q. So k into minus q divided by R2 plus potential due to minus 2q. So k into minus 2q divided by R3. R1, R2, R3. You can blindly add it. You don't want to bother about the direction. This is something called superposition principle. Okay, in physics, many places we have learned this concept called superposition. Wherever you have an additional factors will be there, you can say superposition principle. Superposition principles are applicable when it is in a scalar quantity or when it is in a vector quantity. Also, this is applicable. So it doesn't matters like whether it's a scalar, whether it is vector for applying superposition. But yeah, in short, you can add it for electrical potential because it's a scalar quantity. Direct addition is possible. But in case of electric field intensity, we should be little alert because we need to take care of the direction. That's what I told. This is little easy comparable to that of electric field and electric charges. Hope you understood. Okay, we will apply all this stuffs while we are doing the numerical questions at the end of the sessions. So hope it is clear to you, this concept also. Understand the concept. We are not at all by hearting any stuff. We are not by hearting anything. Now we have some set of formula, some set of concept with us. Okay. Okay, now we will going to see the next topic. Okay, so next topic is yeah, it is a very concept oriented topic. Okay, so write down electrical potential due to a ring. Electrical potential due to a ring. I'll tell you, we have a ring like this one. We are going to find out electrical potentials will be here. Hope you remember, we also find out the electric field at this point. Okay, due to a ring of charge plus q will be here. Then what is the electric field at this point? You remember this formula. At this point, electric field will be equal to kqx divided by r square plus x square whole power 3 by 2. We have learned some formula like this one, right? X is the distance from here and r is the radius of this one. Okay, if you are not remembering, no problem. Go to the notebook. We all human beings, we can't remember everything at a times. So sometimes we may forget. No problem. Now I repeat it again. You can go back to your notebook and check and learn it once again for the next 5 to 10 minutes. You can pause the video and you can learn that stuff. You can go through that. So later time you will remember that. Okay, then you can come to here. So this is the electric field formula. So I'm not going to electric field will be here. My intention is to get the potential. Okay, so what we will do to find out the potential will be here, potential over a ring. So as like we have done will be there. So if you go to that electrical field intensity, pause the video, and if you refer that and if you come back to will be here, that will be very effective. So please pause the video for a next 5 minutes and go to your electric field intensity where we have derived it for a ring in your notebook, and just to refer, just to learn for the next 5 to 10 minutes. Then you can come back to here. Okay, just pause the video and come back. I will also will be with you. Okay, so here okay, hope now you have paused the video and you have got the control will be here. Okay, so there we are assuming a small, so q is a total charge on the ring. So there we have like if you see that notebook, you can see that there are, we have taken this electric field intensity like this, electric field intensity like this, then these components are cancelled, then these components will be added and we are integrated. So there are some vector resolving will be there. So one vector is like this, one vector is like this, this is splitted into horizontal and vertical, this is splitted into horizontal and vertical, and we are doing here no such headaches. What is the distance will be here? Root of r square plus x square. So that's the small potential dV, total potential is V, small potential is dV because of integral k into dq divided by r. R is the distance. What is r will be here? Root of r square plus x square. That's all. Okay, so we'll take the common terms outside, k into root of r square plus x square, integral dq. What is integral dq? Q. Okay, integral dq means q. So kq divided by root of r square plus x square. This is the potential due to a ring. That's what I told. This is very simple because the major headache of vector stuffs are over. We don't want to bother about the direction. This is an electric field due to a ring at a distance of x meter away. Now here I am asking you one question. What is the potential at center? Potential at the center means what will be equal to 0? X will be equal to 0, right? This point is at the center. So what is the value we'll got? Kq divided by root of r square, which means Kq divided by r. Remember this point also. Okay, so potential due to a ring is very simple, kq divided by root of r square plus x square, and potential at the center x is equal to 0, kq divided by root of r square, so r square become r. Okay, next, so hope you understood this concept. Now we have learned few concepts before, work done and ring. Now we'll connect all these topic in a common platform and we'll do one conceptual stuffs. Okay. Okay, what is that conceptual stuff is like? Okay. Okay. I have a ring like this. I have another ring like this one. Okay, this is just an example. We'll put an example number 1 now. Okay, this is at a distance of r meter away. This is at a distance of r meter away. Center to center distance is also, you can assume, r meter. This will have plus q charge. This will have minus q charge. Okay, this will have a charge q0. This is called ring 1. This is called ring 2. Okay, now the question is, the work done to move the charge from ring 1 to ring 2. Work done to move the charge from ring 1 to ring 2. To move a charge, I need to move a charge. Work done to move the charge, in bracket you can write q0. Work done to move the charge from ring 1 to ring 2. Ring 1 to ring 2, I need to move the charge from work done to move the charge from ring 1 to ring 2. Ring 2 center. Okay, we can make it a little more clear. Ring 2 center. Now it is already on the ring 1 center. I need to move the q0 amount of charge from the center of the ring 1 to center of the ring 2. How much is the work I have to do? That was a question. How to do? So we need to move to ring number 2. Final position, final potential minus initial potential 1 equal to work done from 1 to 2 divided by what is the charge I am moving? q0. So what we need to find out? Work done used to be find out, which means this value I have to get it. Correct? That was a question. So this value I have to get it. So I am clearing the board. Then I am moving. So I need to get potential at 2. I need to get potential at 2. I need to get a potential at 1. So what is potential at 2? Potential at 2. At 2 means this position. At 2 central. So here if I am looking, look into my fingers always. Okay, let me make this to be clear. Here I need to find out potential at 2. So potential at 2 means there are two static charge effect we have to see. This is a moving charge. This is already there. So you forget about moving charge. What are the static charges? Plus q and minus q. So potential due to plus q at this point and plus potential due to minus q at this point. What is potential due to plus q? Potential due to plus q means it is at the center, right? At the center. What is the electrical potential at the center of the ring? Kq by r. Okay. Now potential at minus q at a distance of how much? So k into minus q divided by root of, what is the formula will come? R square plus x square. For the ring number 1 at this point here, this is our x distance actually. Okay, so what will come? R square plus x square. X square means again r square. Okay, so we can simplify this factor. So kq is taken outside, 1 by r. Okay, kq will be, here it is 1 by r. Here how much will come? Minus 1 divided by root 2 times of r will be here. So V2 we find out. We'll keep it there. Now we are going to find out V1. We need V2 and V1. So I'm clearing this board will be here again. Okay. So we are going to find out V1. So now you have to place your pen will be here. Now you are at V1. So potential at again both of the charges, potential due to plus q plus potential due to minus q. What is the potential due to plus q? From here, okay, this is a plus q. From here to this point means kq divided by due to plus q. So we are finding here. So this is for a ring at a distance of x meter. So root of r square plus x square. X square means r square plus potential due to minus q. It is for minus q, for this it's at the center. So which is at a distance of r. So kq divided by, so what is coming will be here 1 divided by root 2 r minus 1 by r. That's all. Now we have to find out potential at 1 to 2 we are moving, right? So we are going to find out V2 minus of V1 first. What is called V2? V2 is there, right? We will expand that. So kq divided by r V2 and minus kq divided by root 2 r. And minus of V1. V1 means kq divided by root 2 r. This is plus, another one is minus. So kq divided by r. So what are things will be get cancels? Kq by r, this minus become plus. So 2 times of kq divided by r, this minus and this minus. So minus 2 times of kq divided by root 2 times of r. We got this one, the potential difference. You have to pause the video, you have to write it along with me. Now we find out the potential difference. So I'm clearing this side of the board, and what we need to get it, we need to get it the work. So V2 minus V1, work is from 1 to 2 is equal to potential difference V2 minus V1 into the charge Q0. So V2 minus V1 we already got it, 2kq divided by. Okay, so 2kq divided by r is a common factor. You can take it outside. So it is 1 minus 1 by root 2 times of q0. This is the answer for this one. This is the answer for this one. 2kq divided by r into 1 minus, okay, here 2 by root 2. 2 by root 2 means we can simplify, 2 means root 2 into root 2. So we can written as 1 minus root 2. Correct? 2 and root 2. Okay, 2 is taken outside, right? Okay, then this is correct. 2 is taken outside, so 2kq by r will come, then it is 1 by root 2. Sorry, it is correct only. I thought I have taken kq by r outside. No, I have taken 2kq by outside. So 1 minus 1 by root 2 into multiplied with that moving charges. You will get the work done to move the charge from 1 to 2, from one center to the another center. Hope you understood how to find out this work done and how to find out the potential also. Okay, hope this concept is clear. Okay, we'll going to do one more examples to make its concept is clear. Okay, suppose if we have a rod which contains q coulomb of charges, I have a distance will be here L meter away, and this is also a length of L meter. This is a point P. The question is like, I need to find out the potential at the P. Here q amount of charge will be here. This is a rod. This is a rod. Okay. So the question is potential at P due to the rod due to the rod which has uniform charge density lambda and has the charge q. So potential at P will be equal to, how to find out? This is a rod, so here every point we have a charges. So what will do? If it is a point charge, if it is just one charge, then I can say it is kq by, okay, suppose if you consider here one charge at L meter away, what is the potential at this point? Kq divided by L, you will say like this, kq divided by L, you will say like this. This is for a point charge, this is not a point charge. Here everywhere it contains the charges. So I cannot consider this as a point charge. What should I will do? I will take a small strip will be here, as like if it is a continuous charge distribution cases and whose length will be equal to I can say a dx segment length will be here. So potential at P due to the dx will contains dq charge. So what can I say? dk into dq divided by dx. And we have to integrate this dx or this dx, or which is at a distance of x meter away, and this x is varying from where? Initially it is L and we have to go to till another L. So the limit of integration from 0 to L. Okay, so kq divided by the distance will be here, how much? X distance away. Okay, so this dq charge will be here at a distance of x meter away. So the potential will be equal to integral 0 to L k into dq divided by x into dx. Because why? Because this dx is varying from x. This x is also varying. X is varying from where? This is a starting point. I have to go to till this point. Starting point is L meter away. Final point is L plus 2L. So I have to move from a distance of L to 2L distance away. I have to move towards a distance of L plus 2L meter. No, dx will not come, right? What is the formula of electrical potential? General formula kq divided by r, k into q by distance. So k into dq by x. X will be changing from where? L to 2L. Let me make this to be clear. L into 2L, distance is varying. Okay, so now we'll see. Okay, now what is lambda for this one? Lambda for this segment, charge divided by distance. What is the distance? Here dq charge will have a distance of dx charge. Okay, dq charge will have a distance of dx charges, or I can say for the total body, if I have considered, lambda will be equal to charge divided by its length L. So for dq amount of the charges, we are replacing Vp will be equal to k into, for dq amount of charges, lambda into dx. Lambda into dx divided by x, integration limit L to 2L. This is for full body. This is for the full body. Okay, if you're taking for a dx portion, which contains dq charge, here lambda will be equal to what will come? Dq by dx. This is for that small strip charge by its length. Its length is this much is its length. So dq by dx is called lambda. The lambda is replaced for this one. So remember one thing, whenever you see not a point charge, whenever you see a strip of charges, normally if it is a linear one, then lambda will use. If it is a surface area one, then what you will use? Sigma will use. If it is volumetric one, then you will use rho will be there. That's the difference. Okay, now what all things will be constant? K, lambda is constant, integral L to 2L dx divided by x. Dx divided by x. Balance steps I am filling here. Dx divided by x. Okay, so this is not required. So dx divided by x. So k lambda, balance I am writing here. This is what is called log x. We have to apply the limit L to 2L. Integral 1 by x is log x. So k lambda into log of 2L. Log of 2L minus log of L. So k lambda into log of a minus b is equal to log of a by b. So 2l divided by L. So which is equal to k lambda into log of 2. This is the answer. This is one of the previous year JE main question. This question is one of the previous year JE main question. This question was there. So k lambda into log 2 is the right answer for this question. So it is, we have starting the potential P L to 2L k into dq by x. X is changing from where to where? L to 2L. What is dq? dq is equal to lambda into dx. We are substituted will be here lambda into dx. So k lambda dx by x. This is, we can written in another way also. What is lambda for the whole system? Q by L. So k into q by L into log 2. This is also correct, and this both are same. One and one, this is same. Lambda we have just replaced will be here. No other differences with respect to this one. Kq by L into log 2. Okay. Hope you understood the concept clearly. This is called we are finding the electrical potentials due to a uniform rod at some distance. So uniform rod means charge is not a point charge, it is distributed. What kind of distribution? Lambda distributions, linear charge distributions. That's what lambda is coming to picture. Whenever you, if you see such model of questions, lambda will be there. If it is a sheet, then what will be there? Sigma will be there. Sigma into you have to multiply it with here dx is a length. Okay, in case of sigma will come, you have to multiply it with area. In case of rho will come, rho into you have to multiply it with volume. Whenever if you see any charge distribution, not like a point charge. Point charges we have a formula for potential kq by r. So other than point charges, you have to use a lambda, sigma, rho accordingly. Okay, hope you understand this problem. This is just another examples I told. So first example is with respect to ring, and second example is with respect to this one. Hope both the concepts are clear to you. So then we have to move to the next topic from this area. Okay. Hi dear students, welcome to the next topic. Okay, next topic is related with dipole. Already we have learned about when we hear the term something called dipole, three things are coming to my mind. Okay, of course we know the definition of dipole moment. P is equal to 2L into Q, any one of the charge into distance between the dipole. And three things we have learned in dipole with respect to electric field. The electric field intensity along the axis of a dipole, E is equal to K into 2P by X cube. Hope you remember that. Similarly, electric field at the equatorial position of the dipole, E is equal to K into P by X cube. And electric field intensity at any point due to a dipole, Kp by X cube into root of 3 cos square theta plus 1. Okay, so three formulas will be there. Okay, you can pause this video just for a moment and you can quickly go back to your sessions what we have learned for electric field and dipole. Even though if you remember also, in case if you are not remember also, just to go through that topic for the next 5 to 10 minutes and come back to here. I am not repeating, this is the same story because already we have discussed about the electric field. So you know how to find electric field due to a dipole along the axis, along the equatorial position at any point. Three things we have learned. Just pause the video and have a look into the previous sessions so that you will be getting refreshment, so that then we'll enter into this topic. You will get much more idea about this one. So let's move to this topic. Here we are going to find out potential due to electric dipole. So write down the heading, potential due to electric dipole. Potential due to electric dipole. As what we have discussed with respect to electric field, same thing we are going to learn will be here along the axis, equatorial point at any point. So we'll start with the first subheading, potential. I am writing V due to dipole along the axis, V due to dipole, potential due to dipole along the axis. This is the first subheading. So here we have a dipole minus q and plus q, which are separated by a distance of 2L. From the center, here we are going to find out the electric field which is at a distance of x meter away. This is what we have seen for electric field intensity. The same steps we are going to see will be here also. This is for a potential instead of electric field. So we'll write total potential is equal to potential due to minus q plus potential due to plus q. Here, as I told before, you can directly add it. You don't want to any vector resolving method is not required for potential, because potential is a scalar quantity. That's what we are directly adding this one. What is potential due to minus q? K into minus q divided by distance from here to here, x plus L, and plus k into q divided by distance from here to here, x minus L. Okay, this is a potential due to each of these charges. Kq is taken outside, so 1 divided by x minus L, this become minus 1 divided by x plus L. We have to solve this factor kq into x minus L into x plus L. What will come in the denominator? X square minus L square. What will come on the numerator? X plus L will come here, x minus L will come here. X plus L minus of x minus L. Okay, so we'll move forward. So we got this one. X and x will cancel, L and L get added up. So k into q into what is coming in the bracket? 2L divided by x square minus L square. X square minus L square. Okay. So this is L square, x square minus L square. What is 2L into q? Dipole moment P is equal to 2L into q. This is what we have learned before, right? Dipole moment. So here dipole moment is what direction? From minus q to plus q. So k into P divided by x square minus L square. We know 2L. 2L is the distance between the dipole. The definition of dipole itself, two equal and opposite charges separated by a small distance. So 2L is a small. So L is half. L means just half of the 2L, right? 2L divided by 2, you will get L. So L is again very small. L square means if you are taking a square of a small number, for example 0.1, you can assume L is equal to 0.1. 0.1 into square means 0.01, that is very less. So which means x is much greater than that of L. Compare. So L can be neglected. L in a value, it's very small. So if you are subtracting like 100, if you are assuming x is equal to, for example, x is equal to 10, you are assuming L is equal to 0.1. So x square means 100 minus 0.01 you will get. So this is approximately will be equal to 100 itself, which means x itself or x square itself. Okay, so this is nothing but x square value, right? So we can write Kp divided by x square. This is the potential due to a dipole along the axial position. What is the direction of this potential? We know the direction of electric field, right? The direction of electric field along the direction of dipole moment in case of axial electric field. But in case of a axial potential, what is the direction of potential? No, the statement itself it is wrong, right? Potential has no direction. Potential is a scalar quantity. So Kp divided by x square. In this context, we'll just remember what we have learned for electric field intensity. The electric field intensity along the axial position is equal to K into 2P divided by x cube. We already written this formula, we already derived it, but just for you to recollect it, I have written here. Potential due to a dipole at equatorial position. Two charges minus q plus q separated by a distance of 2L at a distance of x meter away. We are going to find out potential here. So potential V is equal to potential due to minus q plus potential due to plus q charges. What is potential due to minus q charge? So what is this distance? What is this distance? What is this distance? This is root of x square plus L square. This is also root of x square plus L square. Correct? So k into minus q divided by x. The distance is x square plus L square whole power 1 by 2 plus k into q divided by x square plus L square whole power 1 by 2. What is the value of this one? 0. The value of this one is 0, which means potential due to a dipole along the equatorial position is 0, which means there is no potential. What this indicate? This is a very important concept. This is just it is not enough to just to write the formula and saying like that, okay, potential at this point is equal to 0. There is a significance are there. What is that significant means? Okay, so let me take, I have two charges. Okay, one charge will be here and one charge will be here. So two charges will be, one is my right hand, this hand, and one is this pen. So two charges will be here. Now two charges, this is minus q charge and this is plus q charge. If you have placed one sheet will be like this. One sheet will be like this. Let me take my notebook and show to you. This is my notebook. Okay, so what I will do means, okay, so we just, okay, so this is my notebook. I hold it like this. You can see this is my notebook, but instead of keeping like this one, I'm keeping like this one. Now from your point of view, you can see this spiral binding, this area only you can see. So here we have one charge minus q, here we have another charge plus q, which means opposite side, and which are equal distances from this sheet, from this book and from this book. Now what I have seen is like, if you have taking potential at any point will be here. Potential at any point if you are taking, what is the value of this one? 0. So here one charge, so this distance you can measure, this distance is equal to this distance, correct? That's what x square plus l square and x square plus l square is coming in this both case. So if you have taking the topmost point like this, then topmost point like this, distances are equal, charges are opposite, total potential is equal to 0. If you are taking the bottom point, so the distance is almost like this, almost like this. If you are taking the other one, so this is almost like this. If you are taking the topmost point, the distance is like this. If you are taking the topmost point, the distance is like this. If you are keeping the charge maybe at the top, then the bottom, the distance is like this. If you are keeping the charge at the top here, then the distance will be, if the charge is at the bottom, then the distance will be here. So in short, if you have keeping one charge, minus q charge and plus q charge on either side of this book, on here and here, what will happen? Distances from this charge to at any point will have a value. The same distance value will be there for the other charges also, right? If I am taking this point from here, it is 10 meter. Then from that charge also it is 10 meter. If I am taking directly towards sender, then it may be something like some 8 meter. Then from this charge directly to the sender, it is 8 meter. So if you are adding the total potential anywhere, this point, this point, this point, this point, this point, any point, if you are adding, the total potential is equal to 0. The total potential here 0, total potential here 0, total potential here 0. Now if I am asking you, what is the potential difference between 2 points? Potential itself, it is 0. So 0 minus 0, that is called 0. Such surface, such like this. So in that cases, this book, in that cases, this book and the surface is known as equipotential surface. Okay, so this is plane, potential AD point will be equal to 0 because of the two dipoles. With respect to one dipole, it is not 0. With respect to one charge, it is not 0, but with respect to a dipole, it is 0. So potential here 0, potential here 0, potential here 0, potential here 0, everywhere potential is 0. So in that cases, this surface is known as an equipotential surface because potential difference is equal to 0. Potential difference will be equal to 0. In that case, that surface is known as equipotential surface. That is important. Okay, so which means a perpendicular plane to the dipole is having, it is a equipotential surface. So write down a note. This is important. Write down a note. Perpendicular plane to the dipole along the equatorial direction, is an equipotential surface. Equipotential means equal potential. So the difference in potential is equal to 0. Is an equipotential surface, which means, what is the meaning of this equipotential? Highlight. What is the meaning of this equipotential? Equipotential means potential difference potential difference between any 2 points is equal to 0. That point is called equipotential surface, and that surface is called equipotential surface, and the points are with equal potential differences, equal potential. So the difference in potential is equal to 0. So second heading, this is not second heading, right? B, second one, potential due to a dipole along the equatorial position. So this is over. We'll move to the next topic. What's the next topic? You know, right? If as I told while I'm starting this dipole topic, as I told, okay, if you know, like if you have revised the electric field, then the third heading you must know. So potential due to a dipole at any point, okay, at any point, electric field due to a dipole at any point, Kp by x cube into root of 3 cos square theta plus 1. So here we have a dipole minus q and plus q separated by a distance of 2l. Dipole moment is in this direction. I am going to find out potential at this point, which is making an angle of theta degree. Okay, in that cases what we'll do, this p is a vector quantity. P we are splitting along the directions like this, and this component is called p cos theta, and the perpendicular line to this p cos theta. Okay, perpendicular line, because this will becomes as p sin theta. This is p, the adjacent side to theta is called p cos theta. So this line is p cos theta, and the perpendicular one is called p sin theta. So here p cos theta, here p sin theta, centrally it is called p. Now if you have taken the point V will be here, the p cos theta is along the axis and one perpendicular component will be there. So total potential will be equal to axial potential plus an equatorial potential. What is the axial potential formula? Kp. So what is here p? Along this axis, this is the point I need to find out potential. So in the same direction, what is the value of this one? P cos theta. So Kp cos theta divided by x square. X is the distance from this point to this. X is the distance from here to here. X square. And potential due to equatorial. So here p sin theta is perpendicular to this point. This is the plane, and p sin theta is perpendicular. So what is the potential? 0. Equatorial is not giving any potential because equipotential plane is a equipotential surface. Equatorial plane is an equipotential surface. Equatorial plane is a equipotential surface. A term confuse our. You are not supposed to confuse that term. Equipotential surface. Equatorial plane. Okay. Equatorial plane. Equatorial means perpendicular. Perpendicular plane to the dipole is an equipotential surface. It is a true statement. There is a chance to ask this question for your entrance examination. Which of the following statement is true? Axial position of a dipole is an equipotential point. No, wrong statement. Equatorial position of a dipole is an equipotential surface. Yes, that's the right statement. So remember that point. So here total potential V is equal to Kp cos theta divided by x square. Now we'll see what is the potential along the axial potential. Axial potential is what? Axial potential. Axial potential, what is the value of theta? Theta will be equal to axis. Axial theta equal to 0. So what value will get? Kp by x square. This is what we have learnt. In case of an equatorial position theta will be equal to 90 degree. If you substitute 90 degree will be here, what you will get? 0. So this is hold valid, this is hold valid, and this is a general expressions to find out potential at any point due to a dipole. Okay, so three topics we have learned. Potential along the axis, we have a value Kp by x square. Potential at any point, Kp cos theta divided by x square. Potential at equatorial position is simply 0. Hope you understand these three topics. Okay, so we'll move to the next topic then. Hi dear students, we'll move to the next topic, and which is the relations between electric field and potential. So write down the heading. Relation between electric field E and potential difference. Relations between electric field and potential difference. What this means to us? We have learned about electric field. we have learned about potential. What is called a potential? The simple definition of potential is the work divided by charge. V is equal to W by Q or KQ divided by R. This is a very simple definition. So, and now we are going to see relations between electric field and potential difference. Okay, there are two cases are here. We are going to find out what is the relation connecting between, you have to listen my voice very clearly, what is the relations connecting between electric field and potential. Two cases will be here. We know electric field will have two varieties and two flavors are there. One is electric field is uniform, another one is electric field is non-uniform. So in case of electric field is uniform, what is the relations between them? If it is non-uniform, what is the relations between them? That is the intentions will be here. Okay, so the first subheading, when electric field is uniform, what will happen? This is what we are going to discuss. Okay, electric field is uniform means same lines, same things will be here. Okay, so this is electric field. If you have a charge will be here Q, then it will experiences a force called QE. Okay, now I am considering like 2 points will be here on the same lines, positions number 1 and position number 2. Position number 1 and position number 2. If I want to move from one point to point number 1 to point number 2, okay, I am doing a work from point number 1 to point number 2 to move the charge, Q amount of charge I am moving. Okay, in that cases I am doing some work, and that work divided by this charge will give rise to a potential. So I am doing an external work in opposite direction of electric field. Now if you have writing V2 minus of V1 is equal to work done from 1 to 2 divided by its charge. Okay, what is work done? I am assuming this is an electric field created by a charges of capital Q. So V2 minus of V1, this is nothing but it is called a potential difference. Okay, so this is nothing but which is called potential difference. What is work done? External force in this direction. External forces in this direction which is acting in this direction, and because of this electric field the blocks will moving through a small distance called dr. Okay, if you are considering a small distance it is moved, I don't know what is the value, this dr may be a small value or higher value, but at the moment if for this small distance it is moved a distance of dr, then F dot S means dr. External force like this, displacement is like this, angle between them cos 180 degree divided by charge. What is the external force value? External force will be slightly greater than the QE force. So I can say F external is slightly greater than or equal to the QE force, external force. So I can equate this QE dot dr into cos 180 is minus 1 divided by the charge called Q. So Q get cancelled. This V2 minus V1, this is a potential difference between the 2 points, right? Potential difference. I have written a heading called difference. Difference means the change. So this is I am written as delta V is equal to E dot dr minus. So minus of E dot dr. This is the relations connecting between the potential difference and electric field. See the heading, relations between electric field and potential difference. So potential difference delta V is equal to E dot dr minus E dot dr. Okay, here dot products will be there, and we have given a cos angle. So always the cos angle will be matters if you have taken the correct vector format, because we know this is a vector quantity, this is a vector quantity. If you are multiplying with the two vector quantity, we will get a scalar quantity. So delta V is a scalar quantity, electric field is a vector, and this is a vector. So here it is E dr. Okay, this is a magnitude format, this is a vector format. In case of magnitude format, we know minus will not comes will be there, so it is E dr in case of a magnitude format. So when electric field is uniform, the relations between electric field and potential delta V is equal to E dot dr. So this formula is important, minus E dot dr. Okay, this is one point. And the another difference which means I am, you can see I have taken 2 points will be here. Here we are going to write one important point. V2 minus V1. V2 minus V1, if you see, will be here. What you are getting? V2 minus V1, you are getting a negative value. If you are getting a negative value, means V2 is higher or V1 is higher. Can you tell me? If you are getting a negative value, here E dot dr, we are getting a negative value. Okay, higher or lower, let me keep it like this. Here 1 to 2, work is doing from 1 to 2. 1 to 2 means from 1 to I am doing a work. Why I am getting a negative charge? Because I am doing a work opposite to the direction of electric field. Okay, that's what we are getting a negative signs for this electric field, and this will be applicable when the relations between E and the potential difference when electric field is uniform. Okay, then we will write one important aspect here also. Okay, so now I am considering a point like this one. This is the reference point. This is a reference point. From here we have some electric lines will be here. So from here, suppose at 1 meter distance, suppose at 2 meter distance, suppose at 3 meter distance, here charge Q will be here. What is the potential at this point? I can say KQ divided by 1 meter. This is the direction of electric field. Here I can say it is KQ divided by 2 meter. Here I can say KQ divided by 3 meter. So this is the direction of electric field. So along the direction of electric field, potential is decreases. So potential will be, this is the direction of electric field. So if you are going from left towards the direction of electric field, potential is reducing. So this is an important point, write down. Along the direction of electric field, potential is decreasing. Potential is decreasing. Along the direction of electric field, potential is decreasing. Okay, so now we have seen the potential is decreases. Along the direction of electric field, potential is decrease. This is an important point. For example, you may come across some questions might be like this. This is the direction of electric field. Okay, so 3 points I am giving: A, B and C. Where is the potential will be lesser? I can say potential at A greater than potential at B greater than potential at C. Okay, so C is the direction of electric field. So in the direction of electric field, potential is lesser. So C is lesser, B is much more higher, A is very higher. So C, the direction of electric field, potential is higher. This is an important note point you have to write on your notebook. Okay, so then we'll move to do one example to understand this concept best to some clearly. Suppose we have an electric field like this between the two reference point. This is example number 1 from this area, and we have two border lines, and the distances from here to here, it is some 2 meter, and the electric field will be equal to 20 volt per meter. Okay, so the potential at this point equal to 10 volt. This is row A point and this is B point. What is the potential at the point B? So potential at A is given. What are the things we'll get? Potential at A will be equal to 10 volt and electric field will be equal to 20 volt per meter. Distances from this distance vector, this is something, for example, it is called a dr, or we can say simply a distance which is equal to 2 meter. I need to find out potential at the point B. So we are moving from A to B. A to B we are moving. So potential I am writing VB minus of VA will be equal to, or we can start with our general equation. What is the general equations? Delta V is equal to minus of E dot dr. Delta V, potential differences, VB minus VA if I am taking. So VB minus of VA is equal to minus electric field. So minus E. Minus E. Electric field is in this direction. Okay, so our distances from A to B. So A to B is like this. So A to B, we are moving from A to B. So the potential difference is final minus initial. That's what we are writing, VB minus VA. If you have writing VB minus VA means VB is a final point, VA is the initial point. So final point minus initial point. So A to B. So DR is like this and electric fields are like this. What is the angle between them? 0 degree. So E dot dr into cos of 0. What is the electric field value? 20. So minus 20 volt per meter. Dr, distance from here to here is 20. So VB minus of VA will be equal to minus 40. What is the value of VA? VA is 10. So VB minus 10 equal to minus 40 and VB will be equal to minus 30. So VB is equal to minus 30. So the value VB will be equal to minus 30 volt. Okay. Now if you see will be here, this is 10 volt. This is minus 30 volt. So we got the answer potential at B is equal to minus 30 volt. As I told before, that along the direction of electric field, this is the direction of electric field from left to right. Left we have 10 volt is the potential. When we are moving towards right means along the direction of electric field, we are moved how much distance? 2 meter. If you have moved, your electric field value, your voltage value will be equal to minus 30. So this much the voltage is reduced. So this is one example. Some model of questions might be coming some like this. We will see one more example with respect to this concepts. Okay. So example number 2. So the second example number 2. Suppose we have a uniform electric field like this. All are related to uniform electric field. We have a equilateral triangle like this one. Point number A, point number B and point number C. The question is the electric field value is given 20 volt per meter. Again the sides will be equal to 2 meters, 2 meters and 2 meters. Okay. So I'm asking you the question, what is the potential difference between VA minus VB? This is a question to you. For example, you can find any point, but I'm taking VA minus VB. Okay, now we will see what is the things. So first of all, if you have seen from VA minus VB, so VA is a final point. So I am moving like this. Okay, VA minus VB means VA is the final point, VB is the initial point. So I am moving like, so my movement is like this. Okay, so let me make it little easy where you, this is like angle become little more complex to you. Instead of taking like this one, VB minus VA will take. So VB minus VA means I am moving from where VB is a final point. So I am starting from A. So I am taking this direction. So now this is the direction of what is called, this is the direction of motion. This is my dr vector. And this is my electric field vector. What is the angle between them? This angle theta. So this angle is theta means this angle is theta. For an equilateral triangle, angle equal to 60 degree. So VB minus VA, which is called the potential difference, which is equal to E dot dr. So we are finding the potential difference, minus will be here, minus E dot dr. So what is the value of this one? It is 20 minus dr. Dr is this distance. What is the distance will be equal to 2. Angle between electric field and dr vector is equal to cos of 60 degree. So minus 20 into 2 into cos 60 is 1 by 2. 2 get cancelled. What is the value equal to? Minus 20 volt. So the potential difference between A and B, or we can say VB minus VA. VB minus VA, VB minus VA equal to minus 20 volt. Now if you see one beauty of this relation, one beauty, we have to analyze it. It is not like just by hearting the things. VB minus VA, we got a negative value. In this case, VA is an higher value or VB is an higher value or VA is an higher value. Can you tell me? VB minus VA got a negative value means VB is higher or VA is higher. Can you tell me? VB is higher, na? No. If VB is higher means, suppose if you example VB is equal to 10, VA is equal to 2, what you will get? 5. You will get a positive number. If VB is equal to 2 and VA is equal to 20, so VB is negative, so what you will get? Negative value. So if you are getting a negative value, which means your VA will be higher. your VA will be higher. Your VA will be higher. I can say VA is greater than VB. VA is greater than VB. Now if you see, VA will be here, VB will be here, VA will be there, and VB will be here. Okay, so VA greater than VB means along the direction of electric field. So this is the direction of electric field. So potential here will be less, potential here will be more. Okay, this is behind E. This is much more forward to along the direction of electric field. So along the direction of electric field is more higher. Now if I am asking you potential at A and potential at B and potential at C, with this example itself, can you tell me where is the highest potential will come? Highest potential is at A. Okay, so A potential is higher. Next one is what? B potential is higher. Next one is what? C potential will be higher. C potential will be higher. If you so we know VC potential will be higher, right? Now we will see one example. If I am taking VC minus VB, VC minus VB, what should I will get? VC is a lesser value, VB is a higher value. So if I am taking VC minus VB, I will get a negative value. If I am taking VB minus VC, I will get a positive value. So you can pause the video and you can complete this one. So now we will see, we will find one example, which means we are going to find this difference. This difference means I am finding VB minus VC. VB minus VC means I am moving from where to where? VB is a final point. I am moving from C to B like this. If I am moving from C to B like this, then the angle between the electric field and this distance vector we have to see, which means this angle, this is the dr, right? This is the dr from B to from C to B. What is the dr value? 2. What is the angle will be here? This angle is 120 degree, because this angle is 60 degrees. So this angle is 120 degree. So minus of E dot dr. So minus of E dot dr into cos of angle between them is how much? 120 degree. E dot dr, from electric field always you have to take an angle like this. Always you have to take an angle like this. From the direction of electric field you have to turn like this. So E dot dr. So what is the value of electric field? 20 minus 20. Dr is how much? 2 meter. Cos 120. Cos 120 means minus 1 by 2. 2 get cancelled. You will get 20. You are getting a positive value 20. 20 means what? VB is very higher. VC is like this. So this equation is holding true. This concept is holding true mathematically and theoretically. Mathematically and theoretically, which means VB is a higher value. If you are moving along the direction of electric field, potential is reduces. Okay, so here our movement VB minus VC. VB minus VC means final point. So I am moving like this. I am moving in this direction. So VB is a higher value. VC is a lesser value. That's what I got a positive number. Okay, hope you understand the point. Along the direction of electric field, potential is reduces. That is a main ultimate concepts will be here. Okay, so along the direction of electric field, potential is reducing, and if you have taking the value higher value minus lower value, it's a positive value like this. B is a higher value, C is a lower value, so you will get a positive value. So depends upon that in what directions you have taking. Here E direction it is 60, but if you are taking in this direction it is 120 degree. So you can find any answer. You can find VA minus VC. VA minus VC, you will get some value. Okay, so always this kind of model of questions might be coming with respect to the electric field and potential. Remember one point always, along the direction of electric field, potential is reducing. Potential is reducing, decreasing along the direction of electric field. That is important concept will be here. Okay, we'll move to the second subheading under this one. This is a concept from the first subheading. We'll move to the second subheading. Our second subheading is speaking about relations between electric field and potential for a non-uniform electric field. For a non-uniform electric field. Non-uniform means something like this. This is a non-uniform, right? Here if you are taking will be, if you are seeing here, the electric field intensity will be higher at this point. So at this point electric field intensity higher, here at this point electric field intensity will be lesser. Non-uniform electric field intensity strength is not same, it is varying. Okay, it is keep on changing from one point to another point, it is keep on changing, and the electric field strength over an area is changing. Along this line it is not changing, but along this area, at here more electric field intensity, at here electric field intensities are less. So electric field intensities are varying. In that case, what is the relations between electric field and potential difference? The formula is similar to this one, but only difference is minus of integral E dot dr. This is important. Okay, here we know we are taking the potential always from initial point to the final point minus initial point, but here it is initial and this is the final point. This is important. Okay, integration limit from where to where you are moving, that is important. So here you are moving from initial point to the final point. In case of if it is a uniform electric field, there is no integration, simply it is minus E dot dr. And if it is a non-uniform electric field, then you will use initial and the final positions, because normal multiplication and additions cannot be applied if it is a non-uniform distribution or it is a varying electric field. This is a varying electric field. In case of a uniform things, whenever there is no variation, whenever there is a constant things will be there, you can do direct multiplications. Whenever if you see a non-uniformity, non-uniformity in the sense non-uniform electric field strength are varying. If it is a varying cases, we will use the method of integrations. Of course, always you know, right, this is a very fundamental principle in physics. Whenever if you have some changes or you are observing changes, means with respect to time or with respect to distance, if something is keep on changing, not like a sudden change. Remember this statement, this is very important, because throughout the year I will use the same concept will be here. Okay, so three things I will tell you. The point number one, just to understand, we are not writing anything, this is a concept based on mathematics. Okay, so first one, if any quantities which are constant, if you have multiplying like two quantities are exactly constant, that is called uniform. If it is constant, then you can do direct multiplication. Point number one. If it is changing with respect to distance, if you are moving from here, and if it is keep on changing, then you have to use integration. Okay, and you have one point here, you have another point here. Between these 2 points, if there is a sudden or abrupt changes are there, you cannot use integrations in between these 2 points. Between this point and between this point, between these 2 points, if the changes are continuous, you can use integrations with respect to time or with respect to distance. But if the changes are abrupt changes, between these 2 points, you cannot use it. If it is a gradual changes, you can use this method. Okay, gradual changes in the sense with respect to time, there is some change will be there. With respect to distance, keep on changes will be there. Abrupt changes in the sense between this point and this point up to this, no change. Then sudden decreases, all of a sudden decreases, then further no change. So that is a very complex mathematical principle has to apply for such cases to solve this. That is not there in your syllabus, at least to take it forward. Okay, so for you only 2 cases, whether 2 things are constant, you can do direct multiplications, or it is a continuous change, you can use this principle also using integrations. We will see some example for this. Okay, example in the sense not directly an example, but I'll tell you some principle will be like this one. So normally from the question's point of view, electric fields will be given like normally EXI is a vector, right? EYJ and plus and EZK. So unit vectors, because electric field is a vector quantity and the distance is also vector quantity as I told. So DXI plus and DYJ plus and DZK. Okay, Now if you are moving from one point to another point, maybe some initial position minus final positions, so delta V, I am taking VB minus of VA, which is equal to integration from where to where I am moving, A to B, minus of E dot dr. We have to find the dot product of between these two quantities. So what will come? Ex into dx, okay, Ex into dx and plus Ey into dy plus Ez into dz. We have to do this one. So this is one way, and delta V we know. So if you want to find out Ex or Ey, this is a potential. This is, I can say, delta V I can say, or I can, this is also side, I can say dV. So by combining these two concepts, dV, suppose if I am writing Ex, Ex, minus signs will be here. So this is dV. So if you are splitting each terms, I can say minus of dV by dx. Minus of dV by dx is called electric field, and Ey will be equal to minus of dV by dy, and Ez is equal to minus dV by dz. Okay, this integrations when taken to left hand side, it become differentiation. That's what I have done will be here. I splitted this one. This is like delta V, and this is equal to I can say this is one potential, x component of potential, plus this is y component of potential, plus this is z component of potential. So what is Vx will be here? Vx will be equal to minus of integral Ex into dx. Minus sign, take it to left hand side. So it become dVx or dV. Okay, so I can say dVx. dVx divided by dx will be equal to Ex. From here I have written like this one. Integration when taken to left hand side, it become differentiation. So here become dVx will come. Okay, dVx divided by dx will be equal to what will come? Minus Ex. So minus will take into this left side. So we'll get Ey and Ez accordingly. So remember this concept. If they have given to you V, you have to find out electric field, and if they have given to you electric field, you have to find out the other quantities also. Okay, so depends upon that we have to take. So we'll keep it like this, and we will do one example. Questions will be like this one. For example, anything can be given. Let me take one example, one from here, one example from this topic for a non-uniform electric field. Suppose potential will be equal to 2x plus 3y plus z. Potential is given. Find the electric field at 101. Find the electric field at 101. So we have to find out electric field Ex, Ey and Ez. 101 is a Cartesian coordinate system, which means x, y and z will be here. So we are going to find that. So what is Ex? Ex will be equal to minus dVx divided by dx. Okay, so what is the differentiation of this one with respect to x? With respect to x, maybe I'll put 2x square just to understand. Okay, 2x square. Okay, so dv, otherwise it's 2 will come. There is no meaning to apply the points. So the question will be 2x square plus 3y plus z. Okay, so okay, so dvx by dx, if you're differentiating this one with respect to x, what will come? 4x minus 4x because of this minus. Okay, so minus 4x and Ey equal to minus dv by divided by dy. So what will come? 3 minus 3, and Ez, what will come? Minus dvz by dz. What is coming? Z and differentiations minus 1. So the net electric field will be equal to Ex I cap plus Ey j cap plus Ez k cap. Okay, so electric field vector E will be equal to Exi Ex at the point where 101. 101 means what? The value of this is x, this is the value of y, and this is the value of z. I will substitute the value of x will be here, y and z nothing will be there. So minus 4 into 1. So minus 4i plus Ey no need to apply. There is no y term, it's a constant. So minus 3j plus Ez minus 1. So minus 1. So minus 1 into k cap. This is the final answer for the value of electric field. Okay, so electric field is a vector quantity. That's what we have. I cap, j cap and k cap. I, j, k are representing the direction of x, y, z. The same questions may be asked in another way also. Okay, here V is given. Okay, let me keep this question as such it is, but one difference I am going to do will be here. And what is that difference is like, instead of giving V this factor, I am changing this questions to back. I'm giving you example number 2. Electric field is like this, find the potential at this point. Electric field will be given. Electric field will be given means we have to find the potentials at these points. At this point we have to find out the potentials. So to find out the potentials we need 2 points. Okay, so 2 points means find out the potential. Find the potential find the potential between the points. Find the potential between the points 1, 0, 1 and 1, 1, 1. So between the points, between these 2 points, so the potential difference delta V, potential or potential difference actually we are finding. Find the potential difference when the points are between 2 points we need. So we are going to find out the potential difference and we are integrating. Initial point is what? 1, 0, 1. Final point is what? 1, 1, 1. We are integrating 2x square 3y plus z into dr. Dr means what? This is electric field. So I will be there and j will be there and k will be there. I cap, j cap, k cap. So dxi plus dyj plus and dzk. Here also I, j and k. So if you do the dot product between these two, what you will get? Dx square into dx. So we'll continue here. Now this area will clean it up and we'll continue here. So dot product means I with I, j with j, k with k. So we'll continue. Integrations limit from 1, 0, 1 to 1, 1, 1. Initial and final point. So 2x square into dx we have to integrate. Okay, I am splitting the integral. So plus 1, 0, 1 to 1, 1, 1. Next term is what? 3y into dy. So 3y into dy plus next point 1, 0, 1 to 1, 1, 1. What is the initial and final point? Here it is z into dz. So z into dz. So we have to integrate. We have to integrate the first point with respect to what? X. So 2 into what is coming? X cube divided by 3. The limit of integrations we know 1, 0, 1. So this is a limit of integrations, but here the first term is only with respect to x. All others are with respect to what? Y and z. So x only I am keeping. X is from 1 to 1. X is from 1 to 1. Okay, and plus y term 3 into y square by 2. What is the y changes? 0 to 1. So 0 to 1 plus z square by 2. What is the z changes? From 1 to 1. 1 to 1. So if you have 2 into, if you are applying the upper limit minus lower limit for this case, what will happen? The first term becomes 0. Second term 3 into 1 square by 2, 1 by 2. So 3 by 2 minus 0. So it is 3 by 2 plus 1, apply the limits, 1 square by 2 minus 1 square by 2. So it is also 0. So answer is what? Answer is 3 by 2. So 3 by 2 is the value of the potential difference between these 2 points and it is a positive value. Okay, so two things we have to understand. So we know this equations, delta V is equal to integral initial point to the final point and E dot dr. This is a case. If electric field is given to you, you have 2 points will be there. You have to do integrations, what we have seen here. If potential will be given to you, you have to do differentiations to find out electric field. If electric field is given to you, you have to do integrations to find out electric field. So remember this concept just opposite wise. So always remember, in short, V is equal to minus E dot dr when electric field is uniform. When electric field is non-uniform, the potential difference is equal to integral over initial point to final point, from where to where I am moving into electric field into the distance vector.